Hello! Today I'm introducing Statistical Context Detection for Lifelong Reinforcement Learning, our paper at the COLAS 2024 conference. I am Jeffrey Dick, and I worked on this paper with my colleagues Sevtashi Nath, Christos Piridis, Jean Benjamin, Sahil Kaluri, and Andreas Altoggio. We are associated with Loughborough University, Vanderbilt University, and the Alan Turing Institute of the UK. The problem is that there are loads of fantastic lifelong learning algorithms listed on this slide, and many more not listed on this slide. However, these all require task labels. There are special cases, such as task-free continual learning and other replay methods. However, all of these approaches assume that the tasks to be learned do not interfere with each other. That is, that the same observation-action pair leads to different results in different tasks. We introduce SWOKS, a module that sits on top of a neural network learner and detects when a task change has occurred. Then, it provides a task label to the agent, allowing the lifelong learning agent to work in environments where task labels may not be available. Detecting changes. Is it new? Sort of. Detecting changes in a data stream depends on properties of the data stream. Deep RL comes with challenges such as stochasticity, temporal relations, and a large dimension for each data point. RLCD is specifically developed for lifelong reinforcement learning, but is intended for discrete observation spaces. Model-based context detection performs well in detecting task changes in continuous observation and action spaces by utilizing a predictive model, though the predictive model is expensive to train and is exemplified only on a small observation space. OWL, that is continual RL without conflict, detects the current task, but only if it had been pre-trained with task labels. Our algorithm, SWOKS, consists of the following steps. Step 1, compress. Step 2, measure. Step 3, perform a statistical test. It also involves the following considerations: for task redetection and repeated statistical tests. Let's look at step 1. We maintain a compressed history of observations taken from a late layer in the neural network. This reduces the dimensionality of the large input image, whilst ensuring that data considered important by the neural network is retained. Step 2, measure. Older histories of compressed observation data are compared with newer histories, and a distance between the two is calculated with the sliced Waserstein distance. The sliced Waserstein distance is a computationally efficient estimation of the Waserstein distance, which allows distances between distributions to be compared. We store a history of these calculated distances as well. Finally, we use the one-sided Kolmogorov-Smirnov goodness of fit test to compare old sliced Waserstein distance histories with new ones. This allows us to detect when the sliced Waserstein distances statistically significantly increase. Increases can be caused by a change in policy or by a change in task. We reduce the chance of a sudden significant policy change by using a proximal policy optimization network. When the Kolmogorov-Smirnov statistical test returns a low p-value, we assume the task has changed. On to the considerations. The task labeling procedure also involves redetecting previously seen tasks. For each previously seen task, a short history of compressed observations and sliced Waserstein distances is kept. Due to the policy-sensitive nature of reinforcement learning, the agent is redeployed with the policy of previous tasks upon task change detection, allowing current task data to be compared with old task data. This allows previous task labels to be selected or ruled out. The final consideration is the tendency of Kolmogorov-Smirnov to give false positive task change detections on occasion due to repeated applications of the statistical test. We avoid this via the introduction of a beta adjustment parameter, which scales the old slice Wasserstein distances by a factor to reduce the number of false positives. More details can be found within the paper. For our results, we demonstrate in both discrete action spaces with a PPO network and continuous action spaces with an SAC network. In the discrete setting, SWOKS is compared with TFCL to demonstrate the effect of interference. In the continuous action setting, we compare with MBCD, though we use MBCD in the setting without simulated replay to ensure that differences in performance are due to task change detection rather than additional simulated training. Here we can see the task labels generated by SWOKS versus the ground truth task labels in a more difficult to label environment mini-grid. To conclude, we have created a statistics-based task labeling module, SWOKS, that can integrate with any neural network learner, and we show that it's capable of detecting task changes and labeling tasks without pre-training in both continuous and discrete action space reinforcement learning environments. Thank you for watching my video presentation.